We should go full length so that I don't give you stuff enough, more than enough, or more than you can be able to digest. Otherwise, without wasting time, I'm now making a presentation, and we can be able to step back a little bit. I think last time we talked about last time we talked about the working of a centrifugal pump all the way to to a point of establishing what we call specific speed or unit weight. We can calculate or we can compute power, we can compute efficiency, we can also go for NPSH in terms of the atmospheric pressure or based on atmospheric pressure or attitude of a place, vapor pressure, suction head, that factor of safety, and so on and so forth. We have many things to think of, if not to put together. We are not doing this for fun, but this is what you are likely to encounter in practical life, depending on where fate may place you. I don't know where fate will take you, but let me believe that fate will take you to a good place. Okay? Let me believe that so that you can have a good life after all. Let me say that again. So after looking at the working of centrifugal pumps and established all those parameters, we finally talked about speed, power, and I told you, if I can remember, that regardless of what you will ever do, make sure that the suction arrangements, you get them right. My friend, if you don't get them right, you'll be in for a lot of trouble. You'll have messed, and you'll have messed a lot of things. Okay? So that is something not to gamble with. Make sure that even in your own practice, if you're doing any pumping, make sure that you get suction right. Because if it is leaking, you will not raise any liquid. Or if it is faulty and you happen to raise the liquid, chances are that you are going to write the pump off through what we refer to as cavitation. And that is the last thing you should ever think of happening to your pump, regardless of where you are doing the pumping. So without much of whatever, let's talk about these performance characteristic curves, specifically for centrifugal pumps. This is a core thing because from the curves, you can be able to tell how that pump performs without many words. And that's why even in your research, when you go for graphical representations of some things, you are trying to do a summary of very many things so that looking at the curves, I can be able to tell how much is the efficiency, maximum efficiency. I can be able to tell at maximum efficiency how much discharge I'm likely to, to obtain. And if I look at what I call shut off head, which I did tell you that shut off head is experienced when you have started the pump. You start the pump and you close the delivery valve. Let it run at shut off head and see and check whether the gauge will hit the maximum head developed by the pump. Then you open the valve slowly, not quickly, to avoid water hammer. You open it slowly and you see the gauge adjust itself up to the point of operation of that specific pump. That is what we normally do. And that is what I'll expect you to do. So it's regarding what happens with the shut-off head, looking at the curve for power and discharge. You can see it is only the power discharge curve which seem to bear more fruit. When the power is so high, the discharge is so high, okay? When efficiency hits maximum, it doesn't matter what you will do. The thing is, your pump will not be able to pump at a higher head than that, though the discharge may also increase, okay? You can be able to tell that from the curves. And that's why I was saying that it pays to look at the performance characteristic curves for the centrifugal pumps or for pumps, because that tells you a million languages about the performance of the pump. Now, when you go to organizations like Davis and Shetleaves, and let me say you are trying to procure, or you are trying to get a pump from those guys, you've got to be very careful with these curves, because sometimes they don't give you the exact duty point. But to impress you that the pump is still okay, they extrapolate on the performance, they extrapolate on efficiency, they extrapolate on power and other details. And when they do that extrapolation, you find that you have gotten a pump, you have installed it, you are running it, but then it gives you a lot of problems, or you get a lot of problems. Then you wonder, where did you go wrong? And that's why having a knowledge of what is happening when you're using these performance curves is also very important, okay? Because you can tell when you are being cheated. You can also tell when we are not being told the truth. And you can tell also when we are being told the truth, okay? Because what I've discovered is that many people do not understand what really goes on. And because they don't understand what really goes on, you'll always go ahead and give the client, if not the farmer, the wrong kind of thing, you know. Now, when you look at the performance curves, let me say that you can plot a curve for efficiency or manometric efficiency against discharge. You can have it in isolation. You can have a curve for the shut-off head against discharge. You can be able to see that. You can also have a curve of power against discharge in isolation, okay? the case as the case is with these curves. You can have a curve of head against discharge in isolation. But then sometimes, in practice, you decide to combine all of them. You combine all of them in one graph or in one curve, and you see what they can be able to produce for you. What happens when you look at this kind of a graph or this kind of a curve? On the right hand, you have a portion for the shaft of head. We have a scale for the shaft of head, which is the same scale you're using for the head. Okay? You have also a scale for BHP, which is required for shut-off pressure. BHP stands for what we call break, not break, not B-R-E-A-K. There is what we call break. Okay? Up to sometimes we talk about the brake horsepower. Okay? So we talk of the brake. Okay? So I think it is written the same way as brake that we normally use in our cars. But when we talk of the brake horsepower, BHP, it actually is an imperial unit of power, which is equal to 1 horsepower. Okay? But it is only used as a measure of power which is available at the shaft of an engine. That is where you come across it. So we refer to it as brake horsepower. Brake horsepower is slightly larger than the normal horsepower because it will range compared to 1 horsepower. It will go up to slightly more than 1. But we can round off and say brake horsepower is equals to simply 1 horsepower. Yeah, that can happen. So if you look at this curve, what do you see? On the right hand, you have a scale for efficiency, or what we call efficiency scale. And you have a scale for what we call NPSH or NPSHR. Okay? Otherwise, on these curves, you can be able to mark out what we call BEP, which is the best efficiency point. The best efficiency point when you look at your efficiency curves, when you look at your NPSHR or NPSH, as simple as that, and then you can be able to also mark out the duty point of that pump. At the point of meeting, at the meeting point of those curves, how much shaft of head, how much head can you be able to generate? At that point of meeting of those curves, how much is the power in horsepowers? How much is the efficiency? Okay? And these are things that you are likely to see in these curves without a lot of stories. Okay? You are likely to see a lot of information in this on the basis of performance curves. This is part of it. We can also have the characteristic curves of a pump in this kind of a format. Okay? You can have the shaft of head. You can see the shaft of head curve, which coincides with the HQ curve, or head discharge curve, or head versus capacity curve, or discharge rate curve. You can have that. You can have efficiency curve all the way from zero discharge to where it hits the maximum efficiency, eta max. I'm sure you can be able to see that.
Excuse me, sir.
You can't see your screen.
Umeifanyia nini?
Haiko visible, hatuwezi ona.
Umekanyanga waya zangu wewe. Mmoja wenu amekanyanga waya zangu. I know some of you can be mischievous. Can be mischievous. Thank you for that. Can you see them now? Unaweza kuona?
Yes. Yeah.
Good. I'm happy if you can be able to see that. Wacha niangalie nani amekanyanga hii. Kuna mmoja wenu amekanyanga, sijui ni nani. Ama amejificha. Okay, thank you for that then. So I was saying that the characteristic curves will tell you everything as far as the performance of the pump is concerned. And that's why when you lump them in one graph, you can have head against Q, HQ curve. You can have eta against Q curve. Okay. You can have power input curve. You can also have power output curve, and so on and so forth. All these ones you can put them together. And it looks good because at maximum efficiency, you run down to the HQ curve. It will tell you the amount of head you are able to run the pump at. It will also tell you the amount of discharge that you experience at maximum efficiency. It will also tell you the amount of power input at that point. It will also tell you the amount of power output at that point. And that is the beauty of these curves, if you can be able to develop them. And that's why I was telling you that someone can explain anything using a million words, but a graph will tell everything, okay? And that's why even when you are doing your research, I know one day you'll be doing a project. If you can present or make a presentation using graphs, these ones will tell everything because you can understand the trend, what we call the trend. What is the trend of a certain event? How is the trend? Or how is the performance? You see? And if you can get all of that, someone will say this is a good thing, if it is true. And someone will say this is a bad thing. And that's why when you have those guys put in their tenders, during evaluation of tender, or during tender evaluation, you look at the way they have marked these performance curves or characteristic curves. That is where you catch them. You can tell whether the company is using a quack as an engineer or the company is using an expert, depending on the kind of information they are going to put on these curves. Because you tell them clearly, please indicate the NPSH and the duty point of that pump. If the duty point of that pump is at maximum efficiency, you'll be able to know the amount of air it is pumping against. You'll be able to know the power input, power output. You'll be able to know the discharge rate and any other detail that you're looking for. Because below that, you can also have the NPSH curve. You can also tell the amount of NPSH. Out of the amount of NPSH, depending on the attitude you give them, It will tell you whether on installation of that pump, it will experience or it will have a problem of cavitation. Because I told you, cavitation takes place and you write off pumps. Not only even pumps. Cavitation takes place and you write off turbines. I remember some time when Kenya was rationing power. I went to Canberra and I found those giant machines having been cavitated. Actually, they had even removed some of them so that they could fill in what was eaten on the veins using or welding to fill in with stainless steel. That is an awkward thing to do, but what choice did they have? Because the next choice was run that thing at a low efficiency, there's no power production, and once you run it on that, you'll have all the problems. Otherwise, you go buy another one and they're very expensive because they cost millions of shillings. Okay, so you try to avoid all those problems by making sure that someone gives you what you are looking for, okay, and it gives you the correct machine. Then after that, they give you what we call warranties. Some will give you a warranty for 1 year, others will give you a warranty for 2 years. And if someone gives you a warranty for 2 years, when they come and maintain and do everything, then you'll be very happy. Even now, when you are doing all this, you find that someone will give you a quotation and tell you that I'm selling this machine at so much. They should give you the validity period. That price is valid for how many days? In most tenders, those who are kind enough will give you 90 days. Those who are not kind, they are crooks, they'll give you 60 days. Those who are bad enough, they'll give you 30 days. They'll tell you this price is subject to only 30 days. After 30 days, it is likely to go up, but they will not tell you to go down. They will not tell you to go down. Okay? So they have to give you the validity period. They mark every point that you are looking for so that you can satisfy yourself that you have actually bought the right machine. Okay? And this applies to both turbines and pumps. Remember, and maybe I'll mention that when time comes, in hydroelectric power stations, 80% of the works is civil. It's actually civil engineering. It's only 20% which is electrical, electronic, and mechanical. And then there is the social aspect of it, which is not quite engineering, but you cannot ignore it because you have to advocate, you have to deal with the locals so that if the project is within their domain, then they should accept it and accept it as part of that to make your work easy when you're generating power in that area. Anyway, performance characteristic. So this is what we lump together. And you can see at a glance how your pump performs. You can have that, you can also have this. This is another format, but in my opinion, this is good. This is a good way of putting it. This is okay also. You can see head, you can see efficiency, you can see horsepower, output, brake horsepower, you can see the efficiency, and so on and so forth. You can also have this where you have head against Q, you have efficiency, it against Q, input power, output power. You can also have a speed curve. Speed remaining constant, you don't see much change. Otherwise, it's on the same axis. You can have a scale for efficiency, power, and head and all that, but discharge remains discharge on its own. You don't interfere with that because that is our point of interest. Because when you're saying, I want to pump so much, what exactly are you getting at what point? And that's why we talk of the duty point of your pump. You see? So this is how you put them together. Remember, if we split all that, we can have them in this format. You can have an isolated curve for eta versus Q. You can have an isolated curve for power versus Q. You can have an isolated curve for shut of head or head versus Q. But then it is best when you put them together and you have this kind of, let me call it a conglomeration of curves, Okay? It will tell you everything, and you can mark the duty point of your pump. Different companies, depending on what they are doing, will give you different set of curves. These are for centrifugal pumps, okay? And these are for centrifugal pumps when, let me see who is coming in and is stepping on my system again. Okay. Yeah, that is good. Okay. So this will tell you everything, and you'll be satisfied by what someone gives you this. You tell him, my friend, whatever you have given me, come and install it. You do the testing. Then after they have installed and they have tested, not you to install. Your work is to go for commissioning. On the day of commissioning, you call all of them. You call the client, you call the supplier, you call whoever else is a stakeholder, if not a stakeholder, and let them see the performance of that. I remember one time I was doing it for Gilgil Barracks, Gilgil Military Barracks, when I was at your age and had a lot of strength to run around, you know. We called everybody. But a friend of mine had done this. And every time when it comes to design, we used to quarrel. We used to quarrel for reasons I'll not let you know. Were professional reasons. So every time he used to do some things, I knew that he used to do them wrong. But I'll tell him, hujafanya vizuri. So that day we called everybody. Military barracks people, Kenyatta barracks, sijui 5KR, sijui, and I stock theft because they were all being supplied from the same area. And we're all there to see the performance of that thing. When we switched on for pumping to start, nothing came out. We tried the whole day, then nothing worked. And I told him, my friend, you have to do the whole thing, all the way from the intake works, come up with a rising main. Up to that point, where you are supposed to do pumping after the treatment works. Okay? And once he did out what I was telling him, not that I was a better expert, the whole thing worked. And he was very happy. We did another one for Kabarak those days. And one thing I knew is that he did not know how to do evaluation of tender. He didn't know how to do tender evaluation. So he came with a big file in my office. I told him, my friend, can you help me do this evaluation because I'm very busy? I knew he was not busy, but he didn't know how to do it. Then he went away for a couple of days. By the time he was back, I was done. Kumwambia kitu nimemaliza, pea fulani. Hey, you mean you are so fast? Kumwambia that is the best supplier you can come across. And I gave them a brief report. I wrote him a brief report as to why he was the best. Okay? We went to Kabarak, put that thing, and it worked very well. Okay? And that's why I insist. If you're supposed to do something, if you're supposed to know something, make sure that you know it inside out. Unasikia kama? Wapi huyo Kamau nimemwona?
Yeah, nasikia.
Na Abdikadir Mohamed uko leo?
Niko.
Unasikia vile mimi nasema?
Yeah.
Make sure you know something and you know it thoroughly well. Okay? You know the problem with you guys? Wacha niwaambie. When you start looking for jobs, baada ya kumaliza, you want to go, I don't know, to consultancy firms, or NGOs, not NGOs, but parastatals. wish some of you can go to the army because they have got engineering units when they are taking cadets. Those guys don't take anything for granted. Everything they do, you must know it. Because it may mean death or life. Unasikia kuswai?
Yes.
Wacha kuwa mvulana mzini. I'm telling you, must know that thing and you know it thoroughly well. That is what those guys live for. Because anything you do which is not right, it can cost a lot of men or it can cost human life. And that is the beauty of military. If you go to America or United States, there is a United States Corps of Engineers with some of the best professors you can ever come across. I remember when I was doing research using one of the models, we were using a model developed by United States Corps of Engineers. And there was, and I hope it's still useme hatuwezi ukakimbia. Where are these girls? Brenda, unasikia? Brenda. Is Brenda in existence ama ameingia na akatoka? Eh? Where are these girls? Doreen Misaro, unasikia? Doreen?
Yes.
Yeah, you can go to the army. They have they have engineering battalions, which have a lot of serious work. They have a lot of serious work. Yeah? And if the government of Kenya can actually utilize the engineers, the Army Corps of Engineers, they can achieve a lot of objectives. I know they worked on Uhuru Park during the times of Moi. That's why Uhuru Park is the way it is. I don't know who is working on it right now. Okay. Anyway, what I'm trying to stress is seriousness of what you are supposed to do and what you are supposed to know. Make sure whatever stuff you are doing or you are learning, make sure you know it inside out. Anyway, this is still another regiment of that. You can have HQ for the pump. There is also HQ for the pipe. Did you know that? HQ for the pump, HQ for the pipe. Because the piping system has got its own issues also. And you can develop a curve for HQ for the pipe. You can develop a curve for HQ for the pump. You can come up with a curve for NQ or eta Q for the pump. Okay? You can also develop a curve for what we call the systems characteristic. System characteristics curve is what you can see in this one as HF equals to KQ squared. But what is missing in that is it should be HF equals to Z plus KQ squared. What is missing in that is Z. Okay? But you still can be able to mark the duty point of the pump, maximum efficiency, so that you can be able to say, when I'm using this kind of a pipe, this is the amount of head I'm pumping against, and this is the efficiency. When I'm using that kind of a curve, this is the kind of efficiency, or this is the kind of speed that I'm likely to have. You can lump together many things on these curves, and the curve will tell you exactly what you are getting out of exactly what you are getting out of your machine without much hassle. Okay? And that's where the beauty of this lies. You may be given so many stories using 10 pages, fine. But give me these curves. They'll tell me everything in summary form. They'll tell me everything about the pump. Okay? If I go to Short Leaves, I know there are very big, huge booklets they give people. They gave me one. That is okay. They'll give me the big book at 500 pages. But show me the pump you're giving to me from the characteristic curves. That will tell me everything that you are talking about. And that will tell me exactly what I'll be able to get out of that machine. So this is how we go about this, to make sure that we can be able in a simplified and a clear way make a summary of the pump performance. Otherwise, not forgetting, these are the triangular diagrams for the inlet velocity and outlet velocity, depending on how the veins are actually curved. Okay? And still remember, out of that, we were able to explain what each and every term stands for in these inlet and outlet triangular diagrams. Okay? You see that? And we'll still come back to the same kind of formulas when you are doing the performance or you are looking at the working of the impellers or the pumps inside your impellers. Okay? I think we did this. I said, if you go pump running at 500 RPM, I think we did that, if I'm not wrong. Okay? And we have this form of triangular diagrams for the inlet and the outlet. You can see the shaving of the veins and the direction of rotation for this kind of veins in the impeller. You can see this format. You can also see this format. This one, you can see the arrow showing the direction of rotation. This one, you can see the arrow showing the direction of rotation, where you can see all the flow velocities, you can see the relative velocities, and everything else as far as our triangular diagram is concerned. But having understood all this, you still have to come back to this. This is the end of everything, where you actually give a summary of your pump performance, not the complicated mathematics you have with those triangular diagrams. I think we solved this one. We can also have this, you can see, still the same kind of characteristic curves. We have many versions of it. It all depends on the individual. Because if you tell Kamau and Omondi to draw theirs, they will always come up with a different format of this. But the question is, will they be making sense? Okay? Will they be making sense? That is the question. Okay? You can see the efficiency curve, you can see the head capacity curve, you can see the brake horsepower curve, the blind all that. You can put them together and you come up with beautiful things. But again, for you to be able to do this, you can also see in this graph the recommended operating range. What is the recommended operating range for this pump? This pump, you are being told, it can give you slightly over 600 cubic meters per day. Okay? over 600 cubic meters per day, between a range of 600 and close to 1200 cubic meters per day. Okay, if you look at that range, what can you see? It has a maximum pumping head of close to 12, okay? Close to 12, if not 11.75, okay? Or 11.75, or 11.5 meters. That is the head. And it can drop down if you continue pumping more. It can drop down to a head of 6 point something, 6.7 something or 6.6 something. Looking at the maximum efficiency, what can you be able to see? You can see the maximum efficiency of slightly over 70%. Excuse me, slightly over 70% because you put a rule on that and run across to the right. You can tell the efficiency, the maximum efficiency. Okay. You can also tell the power. Okay. You can tell the power. You can tell the efficiency. That is how many horsepowers. And that's why someone cleverly comes and tells you this is the correct or the recommended operating range for your pump. Okay. Which to me is quite okay if that is the correct operating range for that kind of a pump. That is what you'll be looking for. But pin him down to tell you exactly what you are giving me, where is it placed at? Some of them will not like that. You will become too clever. Whatever you are giving us as an organization, where are you placing it at? Okay? They'll tell you where they've placed it at. And if you understand these things, that's why I told you you can understand, you can know whether you are being cheated or whether you are being told the truth. This could be performance cars for a low lift pump, because you can see the pumping head is not more than, it is not even reaching 20. Okay? That means it's a low lift pump, and even the horsepower is not so much because the scale goes up to 6. The efficiency is okay, it goes up to 100 because that is something that you actually expect out of a good performing machine. Okay? Then after that, I think we talked about all this. The pump specific speed, we made all the definitions for geometrically similar pumps, blah, blah, all that. And we showed how we can be able to come up with pump specific speed, which is dimensionless. Okay? Pump specific speed still, until we found that n squared equals to h 3 upon 4 of upon q. So you can get n out of that. And with the pump specific speed, say n is proportional to h upon 3/4 of h, or h raised to power 3/4 by the square root of q, or n equals to kh 3 upon 4 of h. I mean, n equals to k by h raised to power 3 upon 4 square root of q, where k is a constant, and all that. Then from there, we run a summary of the same. Okay, performance characteristic curves. Otherwise, in a generalized form, power for these pumps is given by rho GQH by eta. And I told you that is in watts. You can convert that into horsepower by dividing, when you divide by 750 or 747.75, I mean 71 to be precise. Okay? Otherwise, so these are stories, but we have done the core thing. Any questions on that? Gentlemen and ladies? Anyone with questions on that? So if you have no questions on that, let me share these notes before I forget. Okay. Let me share with this gentleman here called Victor Desmond Tutu. Having seen or having done the pump characteristics, curves, we come to the end of centrifugal pumps unless we look at the nitty-gritties of these centrifugal pumps. And what are the nitty-gritties? Let me see whether I have any summary. The nitty-gritties, which you need to be exposed to. Let me send the notes first to Mr. Desmond Tutu, our good bishop. Okay. To Desmond Tutu. This is LNS. LNS centrifugal pump. Pump curves. Centrifugal pump curves. And yet to you and me, you're all, including me, say please find. Okay, let me see what I'm calling that. Characteristic curves. Please find this attachment. Okay. Okay. I've sent that to Desmond. Okay. Send that to Desmond Tutu. Before that, I also have a special presentation on the same. This one I may not talk much about it, but if you want further reading, I can share this. Okay. So if you're interested in further reading, I can share this. Okay. Because you can see still on centrifugal pumps, talking about the impellers and many details. Then in color. Then the arrangement in the impeller case, in the pump case, in the impeller, the eye of the impeller, they call it pump, suction, the wood valve and the strainer, delivery valve and delivery pipe and all that. Then we have the details of the casing. That is a diffuser casing with a fluid inlet, guide vanes and impellers. And we talk about the casing a little bit more. This is in color. Then the suction pipe, which connects to the center of the impeller to sump, from where the liquid is being lifted by the suction pipe. Then you have delivery pipe, which is connected to the outlet of the pump and delivers the liquid to the required height or to the desired height. Then we have a classification of these centrifugal pumps, still the same thing, but in this case, slightly a different approach. You can see the volute type, the user type, and you can see more details still on the same. On the first diagram, where you have the volute chamber, the suction, the impeller high, the impeller, and the discharge, all those arrangements. Where we say shape and type of casing, either volute or diffuser, vortex or volute casing with guide blades. Here we have the impellers, whether shrouded or what we call closed type or the open type of impeller. And this is how they look like when you would like to see those differences of shrouded ones and open ones. The ones which are made of stainless steel, the ones which are made of cast iron. And I told you, nowadays they're making some which are made of, they're coming up with some which are made of plastic. But the problem is, we have areas like in Rift Valley where the waters are hot. The source of water is a hot one. It's a hot water thing, you know. How do you cope with the plastic ones? You have to go for special type of impellers, and you have to specify that in your tender documents so that whoever is supplying should know it is Kabarak or it is somewhere in the Rift Valley, and some of the details in the Rift Valley which is supposed to know, they should know. Because the Rift Valley can be very tricky. Okay? It can be tricky in the sense that even up to today, Nakuru is still very, very unstable. I was there not long ago and I was wondering how people have come up with those sorts of structures. Then they know very well that Nakuru is very unstable. I've never seen such an unstable town, geologic-wise. Okay? Those who come from Nakuru, those who go to Western, as you leave Nakuru town, there's a time the ground sank with a kiosk. When guys were taking tea in the morning, they took off and left everything there. They left the mandas and the tea. And it took the Minister of Works almost 3 to 4 weeks to fill in that hole. That is Nakuru. It is Nakuru if you go to the Menengai area on the northern part. You come across what in geology you call faults and the cracks. You can see them clearly, very big faults on the ground. You talk to the locals, they tell them, you hear a farmer tell you, my cow entered into this and it disappeared forever. I never saw it again. Okay? So Nakuru is very interesting. So interesting in the sense that even when you are supplying these kind of machines to Nakuru, find out the quality of water. Is it hot? Is it cold? But give them the right thing, because you can mess them up if you give them the wrong impellers and the water happens to be hot, or it changes to be hot with time. You never know what volcanic activity may take place and change that. Okay? And that's why I say, for example, the Menengai is dormant, it is sleeping. One day it may wake up, though with a lot of drilling for geothermal energy. I don't know whether they have been able to relieve the area of pressure, or it is still confined below the earth crust. I don't know. Work done by the centrifugal pump, still on the same. You can see these kind of details. The VFs, the VRs, the betas, the alphas, and all that, so on and so forth. Inlet diagram, triangular diagram, outlet, triangular diagrams. They use all those details. Okay, D1 diameter, okay, of the impeller. Don't worry about the typos, but look at the stuff. Okay, angular velocity, 2 pi n by 60 radians per second, or revolutions per second. All this, still talking about the same thing. And then I have an example of centrifugal pump to discharge 0.18 cubic meters per second at a speed of 1450 RPM against the height of 25 meters. The impeller diameter is 250. Its width at the outlet is 50 millimeters and manometric efficiency 75. Determine the vane angle at outer peripheral of the impeller. Then you have question 2, still on the same. And then still the same question, head of centrifugal pump expressed in the following ways. You can express the head as a static head, manometric or total gross efficient effective head. Static is the sum of suction head and delivery. That is what you call static. Manometric head, the head against which the centrifugal pump should be able to work. Okay. The next question also, another question. They have several of them. Total gross effective head, which is equal to the static head plus all head losses occurring in flow before, through, and after the impeller. Losses and efficiencies of centrifugal pumps. Okay, you have what we call hydraulic losses, mechanical losses. That's why we talk of hydraulic efficiency, mechanical efficiency, hydraulic, and heater mechanical. All these you take them into consideration. Effects of variation of liquid flow rate on the head. Okay, manometric efficiency, eta mano, and the volumetric efficiency, eta V. There are all sorts of efficiencies. Okay, then you have mechanical efficiency, eta mech, and overall efficiency, eta not overall efficiency. You can see how you can get overall efficiency. And then looking at the minimum speed for starting a centrifugal pump, still also have these kind of details. All that, pump efficiencies. And another example still. Okay, all these examples, design considerations of centrifugal pumps. I talked about the speed ratio, flow ratio. All this come across it. Then specific speed, which we did address, where Q equals to pi D1, B1, VF1 equals to pi D2, B2, VF2, blah, blah, all that kind of thing. You have done mention that. And then you talk of the specific speed equals to speed square root of Q by manometric head H raised to power 3 upon 4. Okay. Amount boiler feed pump is required to pump. An example for you. Okay, maximum suction. Lift or suction height. You consider your centrifugal pump with a lifting liquid from a sump. And you can see the arrangement on how that is happening and the equations which are linking that kind of an exercise. Okay. Suction lifts, NPSH. That is the difference between the net inlet head and the head corresponding to the vapor pressure of the liquid. And that's why I told you, NPSH is very important. Can also be defined as the net head in meters of liquid. That is required to make the liquid flow through the suction from the sump to the impeller. This NPSH is equal to the absolute pressure at inlet of pump minus vapor pressure head plus velocity head at inlet of the pump. That way you should be able to get to NPSH. In other words, NPSH is P atmospheric upon rho G minus in brackets velocity, or rather minus Vs squared, that is on the suction side, divided by 2G plus Hs on the suction side, and HFS minus Vp for the vapor pressure upon rho G plus Vs squared upon 2G. Sometimes you find elements like also. But I told you, in pumping, you don't ignore anything because it is what you ignore that will make sure that you don't get to a liquid. Okay? It is what you ignore which will make sure that you don't get to a liquid to where you want it. And that's why you pitting it against atmospheric pressure, NPSH is equals to atmospheric pressure HATM minus HS, HFS minus HV. Okay? The only thing they have not put in this is HLS. There is losses in the suction. So take that into consideration. Okay, so that you can be able to get your NPSH, net positive suction head. All these additional notes. Then cavitation is centrifugal pump. When does it begin to appear? When the pressure at the suction falls below the vapor pressure of the liquid. Okay? And you find it actually increases with a decrease in the value of NPSH. That's why I told you NPSH is very important because there is a detail I'm not going into what we call the TOMA. You apply what we call the TOMA cavitation number. You come across the TOMA cavitation number in serious designs. And when you take into consideration the TOMA cavitation number, I believe should be the same TOMA in such tanks, because there is a TOMA formula or equation for design such tanks. So talk of the TOMA cavitation factor. You see, it is a dimensionless factor you'll be able to apply. Okay? Why do you apply it? So that you can be able to predict or possibly you assess whether there's likelihood of cavitation in hydraulic pumps and turbines. Actually, is denoted by eta. Not eta, sorry. It is denoted by sigma. Okay? And sometimes you say sigma C for the TOMA cavitation number. It is given by what? Huh? I don't know. Let me see where I can place it. Oh, let me minimize this. There's a gentleman called Dietrich Thoma. Say Thoma was a German engineer. Thoma, we call him Thomas. Thoma cavitation number. Let me give you that. Though I've already shared this, but you can edit in your notebook. Then you transfer to that because you can edit my notes. Tuko pamoja kwa hiyo. Call it Thoma or Thomas cavitation number. Let me see what I can insert with that. I have a symbol for sigma. Yes, I do. I call it sigma C equals to what I'll put in here for you, or what I'll put in here for us. Say it's 0.044, 0.044, Okay, let me see whether I can put my brackets here. 0.044. Let me minimize this. Should not deny me what I want to give you guys. I want you to be the best there can ever be. If you're the worst there can never be, then I don't want to see you. Let's get Desmond. Desmond. Desmond.
Yes, I'm here.
If you're not going to be the best you can ever be, I don't want to see you again. Yeah? Because I would like you to talk with confidence. Say, my name is Desmond Engineer, Desmond Tutu. And I'm schooled properly. Huh? Huh? Nasikia Abdi Kadir. Abdi, are you there?
Yes, yes, I'm here.
Hata ukienda kuuza ngamia waambie, my name is Engineer Abdi Kadir. Unasikia? Waambie wasikuone hivi hivi tu. Lakini usiwaambie sana kwa sababu they tell you wewe ni engineer lakini huna pesa. Hata yule jamaa anakusomesha hana pesa, yeye ni maskini. Tell you the guy is very poor. I don't know why people use that term, as poor as a church mouse. That is for, actually this is for turbines. Okay. There's a Toma cavitation number for turbines, denoted by that for the net positive suction head. Let me save cavitation factor for pumps. Okay. Cavitation factor, it is almost, actually it's the same thing. The only thing is, where do you apply it? Okay. Where do you apply it? Is it into turbines? Is it into pumps? Okay. So these are things that you cannot be able to ignore. Otherwise, what I've given you for this is more or less like what you may use for pumps. But I told you, pumps and turbines, they are cousins. Because one is a reverse of the other. Okay? One is a reverse of the other. And even if it's a reverse of the other, we can be able to share the knowledge. Because if you look at that centrifugal pump and a turbine, we have axial flow turbines. Do you want mixed flow turbines? We have reaction turbines and impulse turbines. Okay. Oh, you are saying the notes are not yet received. Don't worry, they'll come. Nakwambia your system has a problem, Desmond. Sababu haitaki kupokea.
It's not mine, it's yours. Because
No,
the other notes is patanga.
Mine is okay, Desmond. Which ones are you afraid you may not get?
Because even yesterday we had to resend the link again.
Was it because of me or you?
I think it's on your side.
Oh, you think so?
Yes.
Oh. So you're telling me I should do something about it?
Probably, because I haven't received the notes yet.
So I resent.
Yes.
So hizi zote kiwa hujapata nisitume tena?
Yeah, leo pekee.
Leo peke yake. So the ones I'm calling additional notes, do you guys, are you interested in them? Mama niwache tu. You can see for the critical Thomas cavitation number, sigma C, or Thomas cavitation factor. It's 1.03 by 10 raised to power minus 0, ns raised to power 4.3. Okay, so this is very detailed, and you still have performance curves. Okay, it doesn't matter whether they're in feet or they're in meters, because in this case you can see meters and feet on the right hand side or gallons per minute or something like that. You should be able to convert from one system to another. Okay, and that marks the end of this. So will you be satisfied with the first version, or you want both? Desmond, you want both, or you want one version?
Both.
Najua mtaka kukosa. Mtaka yote kukosa yote. Desmond, mtaka yote kukosa yote. Okay, let me see whether I can forward to you both. But you promise me you'll be the best I can never come across. So that when I meet with the Davis and Shetlif's guys, I'll tell them, gentlemen, I have a group of guys you can use very well. Or Rift Valley Machinery Services. Tell them you have a group of guys who can use very well. And mtu class nimwambie kuna mmoja ambaye hakujangi lakini sitawaambia ni nani. Okay, let me see whether I can resend them again. Let me resend them again to Mr. Desmond. Okay. Mr. Desmond. Let me say LNS for you. Characteristic curves. Characteristic curves. Not characteristic, character. Character, not character, character. Characteristic. Good. Characteristic curves. Say, dear Desmond now, and company. Associates. Please find.
Excuse me, sir.
Yes.
I know why. That's the wrong email. The 97 comes before the art.
Oh.
That's why.
Who gave it to me?
No, the one I've given to you has the 97 before the art.
Oh, so this one comes before?
Yes.
That's Naili talk about P.
You know, CG. But yes, you
But that is what you have been using.
No.
You know, kama vile wanasiasa wanasema.
So even if you check your text right now, I've sent the real email. Okay. That one I sent before one.
Okay, let me see the amount to two.
The second one.
The second, oh, this one?
Yes.
Oh, now it may come, eh?
Yes.
Thank you then. My system is good. Huh? Centrifugal. Mi singejua hiyo. Hii kitu na keep records. Centrifugal pump curves. But anyway, that is a good thing because I could have continued using it and we keep on quarreling over nothing. We should quarrel over something real. Quarrels are good sometimes because you sort out problems. Or not, we call them acting disagreements. They are good because, because you solve problems. Please find the attachments. Okay, if what you have given me is true, let me see whether it can come. And I think it should come. I have the characteristic curves. No, this. I hope this is the right thing I'm doing. Go to Desmond Victor, good. And then let me attach the second version. In a Rafiki. You're not supposed to. I've given you enough. But to consolidate you, in your Rafiki. So when it comes, please make sure you tell me it has arrived. Give it a cup of tea so that you can be happy with it. You don't keep quiet when it arrives. Okay. Imekuja?
Received.
Good. I'll see how to remove that email address ambayo iko at 97 so that I remain with 97 at Gmail. I hope I'll not confuse that again. Otherwise, this is quite practical. This, lakini mtaongezea kwa besides, lakini mtaongezea kwa nini? Hii mtaongezea kwa notes. You write it down, you can edit the notes and unaongezea. In the design manual, you have a design manual. In the design manual, not manual. I'll write it properly. For the design, in the design manual, power is given by what I'll give you here now. I've already sent you these notes, but make a point of writing that down if you wish to. You may find it useful. I don't know at what stage. If you go to Botswana, power is given by QH. Yes. Divided by 102. Divided by 102E. Where I don't like Calibri. And this, I think this should be at 24. Where H is head in meters, E is efficiency, is efficiency. And Q is in liters per second. If you go to the design manuals of the Ministry of Water, this is what will come up. Or these organizations, I don't know whether it's the Ministry of Water or which organization. Put that down it's for your good. Okay. I'm remembering this when I've already sent you the notes. You can say power equals to that. And whatever you get here, I think is still in watts. Let me put the brackets there. Say this is in watts. Though you can compare with power equals to rho g QH by eta. See whether it gives you the same thing. Okay. See whether that gives you the same thing. Edit the notes and put that in, if you don't mind, please. So that if Davis and Shatcliffe lands on you and they give you a Pro Box as a sales representative, as a sales engineer, you should be able to perform for those guys. Okay? Now, if you don't mind also, let me add something and say, look at what we call special effect pumps. There's what we call special effect pumps. Is that too small? It should be 24 for me. There's what we call special effect pumps. Which ones are these? Like we have the jet pumps, airlift pumps, jet pumps, airlift pumps. And for once, please have a look at submersible pumps. That is pumps for boreholes. Look at submersible pumps. In fact, these ones you may give me as an assignment.